Welcome to Science 25, Lab 9. Lab 9 is about liquid mixture and solutions. So in this lab, you have to know some keywords. Which one is called solvent, which one is called solute. So solvent is in the solution, which one is maximum amount is called solvent. And which one is small amount is called solute. So that means like if it is salt water or sugar mixing with water. So sugar is the solute and water is the solvent. So in this experiment also we will talk about different types of solution, such as super saturated solution, saturated solution, unsaturated solution, and precipitate. So that one is like white solution. Not white solution, white material you can see at the bottom of the test tube. So also we will see some different techniques to separate different types of solution. So like homogeneous solution. Homogeneous means like you cannot see any layers. It should be like there should be different compound, different material or element. It should be mixed in the solution, but you cannot see any layer. Some of them has defined compound is mixing the solution, but you can see the layer. So homogeneous solution we can use like homogeneous is two solution and the colloidal solution. They are under the homogeneous solution. And there is another one is heterogeneous, which one you can see the layer, and that is you can also say that suspension solution. So you can see the white material bottom of the test tube. So true solution and colloidal solution, you cannot separate it by filtration because you can see any layer, so there is no white thing or any suspension is there, so you can see like with the gravitational filtration you cannot separate those. So what we can do is we use the dialysis, what we will show you in part 1. So as for lab we are using different kinds of chemicals, we need the safety first, so you have to use the goggles and the gloves. So the part 1, we will demonstrate and we will show you different types of solution. So here we will use barium chloride solution, okay, and we will also use the starch. So barium chloride, there is barium and chlorine. So two types of ion, barium ion and chloride ion is inside. So we will use sulfuric acid for investigate that there has barium ion, and also we will use the silver nitrate to investigate that I have the chloride ion. Both of the ion will show you that there is a white suspension is there. White precipitate is over there. So first we will do we need a standard test result so that we can see that after dialysis, because in this dialysis bag inside has barium, chlorine and starch, all of them is together. So we need some standard result so that we can compare after doing the experiment that what is inside actually. Okay, so it says that we have to use 5 milliliter of water. So for barium, I will just use it, and it should be for chlorine. Let's just take it for 5 minutes. Okay. So I will use, for observation, sulfuric acid. We will use the 5 drops of sulfuric acid. So this is for barium, 5 drops. So barium, you can see that is totally clear, the solution. You tell me that when it's done. I'm going to use 5 drops of sulfuric acid on. So as you can see, here has white precipitated. Okay. So this is my standard result for barium. Now let's see for chlorine, chloride ion. For chloride ion investigation, we will use the silver nitrate. Same way we will use, so you can see this is clear, okay? And we will use silver nitrate 5 drops. 1, 2, 3, 4, 5. Okay, this is white precipitate. So we have two results. The saturated standard result for barium and chloride ion. So I'm putting my barium first and then chloride. Okay. And now for starch. Starch is clear. Okay. So I'm going to use iodine. I think the white background is good. So you can see this is blue. Okay. So if I use iodine, the starch getting blue. So these are my standard result for barium, chloride ion, and the starch. Now I'm going to use the dialysis bag. Okay, let me tell you something about the dialysis bag. The dialysis bag, the wall of the bag is made by semi-permeable membrane. So what this done by semi-permeable membrane is it's just only allow certain size of molecules or particles to pass through. So true solution which has the particle size is less than 1 nanometer. Colloidal solution, which is we are going to use as a starch, which is 1 to 1000 nanometer size. So what the wall of the semi-permeable membrane does is it just make a restriction to starch molecule doesn't come outside of the bag, but the barium and chloride ion, as they are small size of the particle, so they can pass through from the bag. So when I will submerge this bag, so barium and chloride ion should be mixed with this water, but only the starch will remain inside the bag. Okay, so we need to make it hard. So I just put it in a hard. Should I put it now? This is water. Hmm? I can do it. Okay. So before I start my reaction or experiment, you can see the solution is totally clear. Nothing no color, right? No color. And I cleaned it with the distilled water so that no other material is on the wall. Okay, so I'm going to submerge it. From this bag, the barium and chloride ion, I'm waiting for to come out outside the water and mix it with the water, and only the starch will remain inside the bag. I will do the same procedure as I did for the standard. So I will take the water and we'll do the three test or experiment to see that which molecule or which ion or which solution is come out. So I came back after 30 minutes to do the hot bath. So now I will check which compound has through from this semi-permeable membrane, the dialysis bag, from the dialysis bag to inside this jar. Okay. So I will take some solutions. I will do the three experiment again for barium, chloride, and for the starch. And also I'm telling you that as whatever the molecule is inside, the barium and chloride ion, right? So this came out to the water, so it diluted more. So the color, the standard result for my hair, okay, so you can see the white participate in here. So barium. So you can see the amount of the barium. It should be less. I would expect less because I have more water in my solution. Okay. Should I wait for cool down or it's fine? Okay. Okay. So first thing I will do for to check barium, I will use the sulfuric acid the same way. So barium. This is my solution from the jar. Okay. So I will use the 5 drops of sulfuric acid. 1, 2, 3, 4, 5. Okay. As I told you, I expected less. So this is my true or this is my standard result in the test tube. And this is my barium. So I can see that there has barium inside. As this was clear and now it is white. Okay. The second one for chloride ion, I'm going to use silver nitrate. One, two, three, four, five. So you can see there is a white. It was clear, now it's white. So I have chloride. This is my after dialysis so result, and this one is my true or standard result. So you can see. Okay. So true, and this is for the after the dialysis. Standard result and after dialysis. Now I'm going to for the starch. I'm expecting that this semi-permeable membrane will not allow the starch to come outside. So I'm going to use my iodine solution to check that I have starch or no. check. I expected blue. I expected blue, but the result come out is kind of clear. This as we have iron, so partially like yellow, but I expected blue, so it's a huge difference. So my iron did not come. Sorry, my starch did not come outside. Okay, because the starch molecule, the particle, is so big than the true solution, so that it this wall, the bag, doesn't allow the starch to come outside. So in this experiment, this solution in the jar, we did the experiment, right? So we can see that barium and chloride ion come outside in the solution, but the starch is not. So what I'm going to do now, I will put iodine in this jar and I will check that my iodine ion is going inside the starch inside the dialysis bag or no, because I'm so our starch doesn't come outside, but the iodine ion, I want to see that can it pass through the dialysis bag or no. Okay, so I will put iodine solution in this jar. My iodine solution in this jar. I will keep it for 30 minutes to see that this iodine pass through to the dialysis bag or no. Let me show you again. My dialysis bag is totally clear, right? So I will submerge it in the iodine solution to see that the iodine pass through the bag or no. So we came back after another 30 minutes to see that what happened if I put my iodine solution inside the jar and my um, ion, it passed through the semi-permeable dialysis bag or no. Okay, so see what happened. So the iodine goes inside. How I know? From my standard result. Remember, we did it with the starch. So starch with the iodine, it gives you the blue color. Now you see, this is with the dialysis bag when I put the iodine inside the jar. Okay, it's the same color. But what happened when we did the hot bath, right? This is the iodine. When it was, this is when I did the hot bath and my barium and chloride ion comes outside the jar, but the starch did not. So that result is this one. So so the starch, it not came out from the dialysis bag, but when I put the iodine, it passes through. So what the dialysis bag does, only the true solution, which one is less than 1 nanometer size, those particles can pass through this dialysis bag. Okay, so you can see this is from the jar. We did it before, that starch did not come outside from the dialysis bag. This is my standard result, and this is when I put my iodine inside the jar to see that it comes through or not. Okay, so this is part one. Under part one, we can see the physical properties of the true solution and the colloidal solution. So true solution, I told you that, okay, true solution and colloidal solution, both are homogeneous. You cannot see the any layer, first of all. And true solution has small particles than the colloidal solution. So that's why when I put the laser light sugar solution is actually the true solution. The particle size is very small. That's why the light, it doesn't give the particle doesn't give the light particles a space to pass through. So you can see that there has no light is passing. But we can see the starch solution, which is colloidal solution, and the particle size is big than the true solution. That's why it has the space to pass through the light. So the light particles can pass through the colloidal solution. So group 1 is about the filtration. Filtration we can do if any particle or molecules is insoluble, then we can do the gravitational filtration. If it is like true solution that is homogeneous, so we cannot do the filtration as we did before the dialysis, right? So for doing this experiment, the filtration, we will use water, and we will use chalk powder. I know that is insoluble, but so I will mix it up. Okay, so still I can see that it's not soluble. Okay, so I will do the filtration in this case. How we can do the filtration? This is the vacuum valve. Okay, this way, the horizontal way is closed. If you want to open it, it should be vertical way. Okay, all the way to here, so I can hear the hiss. Okay, all right. This is the funnel we are going to use for filtration, and this is the filter paper. Before you use the filter paper in this funnel, we have to use few amount of water so that my filter paper stuck. Okay, filter paper sits there so that there has no hole is open. Okay, now I'm going to put it inside. It's a cork which helps no air comes out. So now I'm opening my vacuum valve. This is my, you can see now after mixing it up. So my chalk is at the bottom. There's total clear water. So it's not soluble, it's insoluble. I'm going to pour it. Before I pour it, I want to mix it up again so that my whole chalk powder goes inside. So it's totally, and now I'm pouring it. So you can see that there is a clear water, no chalks inside. Okay, only chalk powder is filtered using my filter paper. Now I want to see, this is called cupric sulfate. This is dissolved. This is totally dissolved, you can see. Okay. Now I want to see that this dissolved cupric sulfate will filter, so it will stay here or it will go inside. That's what we are going to check. Because there is no layer. If it has layer, so we can filter it out. If it doesn't have any layer, if it is soluble, so we cannot filter it. Yeah. So as you can see, this is blue color. My water is getting blue, so I cannot filter it out using my filtration technique. So if it is homogeneous, no layer, we cannot do the filtration. Now we are moving to part 2 and group 2. In group 2, it says that comparing the solubility of different solutes in water. I have 5 test tubes with the 5 milliliter of water. I'm going to use different types of solutes in here. So we have sodium chloride, we have sucrose, we have gelatin, we have oil, and also we have the iodine solution. Okay, what we are going to compare, like we will use the water. Water is the polar, and those we have to see. Okay, solubility, it happens when polar attracts, non-polar attracts, and when we have polar and non-polar, that time it doesn't solute, it's not soluble, and it creates, you can see the layer, or you can see the white percentage. Okay, so we will see now. So first thing is we will use the sodium chloride. Sodium chloride, what is inside has? It has sodium and chloride ion. So sodium is positive ion and chlorine is the negative ion. So it has positive and negative. Water has also hydrogen and oxygen. So hydrogen is partially positive and oxygen is partially negative. So it should be attract and should be soluble. So I'm mixing up. Okay, so I'm mixing it up. You can see there has no layer. So you can see it's totally soluble. There is no layer, there is no precipitate. Okay, so sodium attracts. Sodium is a positive ion. Sodium attracts with the partial negative oxygen, and also chlorine is attracted with the partially positive hydrogen. So it's soluble. Okay. Now we are going to use the sucrose. So sucrose, it should be also soluble. You can see there has no solid in here. Okay. So sucrose, what it does is it interact with the polar molecule of hydrogen and oxygen. So it dissolves in the water. it has no it is not an ionic compound actually, so it dissolves. Okay, now I will do with the oil. So you can see it totally clear. Oil never soluble in the water. You can see a layer, but still I'm going to mix it up. It doesn't dissolve, so I should keep wait to see that the layer come out or no. So I will come back for this. So now I will do the gelatin. Oh, you can see now. You can see now. So here on the top, you can see the layer. So if I give more time, you can see the actual layer. Okay. So water is at the bottom. As the density of the water is high than the oil, so oil is always float in the on the top of the water. Gelatin is a combination of polar and non-polar. So in a room temperature, some of the amount of the gelatin, you can see that it would be soluble, but not totally. Okay, and gelatin is a protein. So it's not totally soluble yet, but we will check. But some of the amount is soluble inside the water. But I will come back. So in a room temperature, you can say that it's not totally soluble. So we will observe in cold water and hot water. So these are all I'm doing it right now is for cold water. So the last one is for iodine. I have 5 milliliter of water, and I'm going to use the iodine crystal, okay, not the solution. So you can see it's at the bottom, never soluble. Because iodine is the non-polar, water is the polar. So iodine, what happened? Like iodine, they have one valence electron. So when two iodine compounds, they use the single bond, and they don't need any more. They don't have any more valence electron to share with the water. So that's why iodine never soluble in the water. The next part we will do for hot water. So this is sodium chloride with the water, no layer. This is sucrose, still doesn't have any layer. You can see a beautiful layer with oil and water. Okay, it doesn't dissolve. This is sucrose. Oh, sorry. This is gelatin. Gelatin with the water, and you can see there is some chunk of gelatin inside at the bottom. And crystal clear, you can see the iodine. It doesn't dissolve. Okay, it doesn't dissolve. You can see the chunk of the iodine. So group 2, what is the purpose? We are going to see that which solute is going to be soluble in the water. So we can see that sodium chloride and sucrose, these are both soluble in the water, cold water. So I'm not going to do the test for the hot bath, but I will see the observation for these three: oil, gelatin, and for iodine. So I'm going to do the hot bath for this only three to check that if something changes in a hot bath, if the temperature increases, if they are soluble or not. Okay. So I have oil, gelatin, and the iodine, and we will come back later. Okay, so we come back after 15 minutes. I wanted to make a hot bath of these three of them, which one was insoluble in the cold water. So now I'm going to check. So this is my oil with the water. Still you can see the layer, right? So that means if you increase the temperature, it doesn't matter. Oil never dissolve the water, because the water is a non-polar. Sorry, water is polar and oil is non-polar, so they don't ever dissolve in water. Okay, so next one, I said that gelatin is a combination of polar and non-polar. Check, it reaches maybe the melting point, that's why it dissolves in our hot water, the gelatin. So in hot water bath, it dissolves the gelatin. Iodine, which one has a chunk when it was with the cold water. You could see the chunk. Now you see it totally dissolved. As the temperature increases, it dissolves. Okay, the solubility is increases. This both the gelatin and the iodine. If the temperature increases, the solubility increases. So sodium chloride, as it dissolves in the cold water, I do not do any hot bath water, but still, if you do the hot bath water, it is still soluble. Okay, so this is for sodium chloride and water. This is for sucrose and water. So both of them in cold water they are soluble. If you do the hot bath, still will be soluble. This is for the oil and water. You can see still the layer. So in the cold water, you could see the layer. When you do the hot bath, still has a layer. The gelatin, it was not totally soluble in a cold bath, but when we do the hot bath water, then it was soluble. As the temperature increases, the solubility increases. And this is an organic compound, guys. This is a mixture of polar and non-polar. So some of them soluble when you do the cold bath, when you mix with the cold water, and it totally dissolves when you do the hot bath. And this is for the iodine. When it was with the cold water, you could see the chunk, but when you did the hot bath, there's no chunk. It's totally dissolved. So melting point temperature increases, the solubility increases. In group 3, we are trying to compare the solubility of iodine, the crystal iodine, in different solvents. So what do we have for this experiment? We have water, we have ethanol, which is alcohol, chloroform, and toluene. What this is in this experiment we are doing is we are starting from the polar and we are going the non-polar. Okay. So iodine, we know that this is non-polar. We are trying to see that what it happens with polar and non-polar, how it's soluble. Okay. So this is the crystal iodine. First, I'm going to put different solvents here, and then I will add my crystal iodine. So first, water. We know that water is polar. Okay. We have ethanol. Ethanol is a OH group. So OH is hydroxyl, which is polar, but CH3, CH2 is a non-polar side. So it's partially polar, you can say. So this is chloroform. And this is toluene. So water, we started from water. Water is polar, partially polar. Then these are non-polar. And we know that iodine is non-polar. So polar, polar attract, non-polar, non-polar attract. That means those are soluble. And we will see that what happened with polar and non-polar, if it is soluble or non or insoluble. So I have chunk of iodine. I will put each of them. Okay. As I put it, you can see that the solubility, the water with the iodine. Still, it's not soluble, but still I want to mix it up to see that in case it's soluble. Still, I can see the chunk of iodine. Okay. Now this one was with the ethanol. Okay. I can see here bottom, but still I'm going to mix it up. So you can see, I don't know you can see or no, but I can see at the bottom it still has some crystal. You can see. So it still has some crystal. So as I said that this is partially non-polar, because CH3, CH2, those are non-polar, but hydroxyl, which is polar. So that's why it's partially dissolved. This is with the chloroform. It's totally dissolved. I don't see any chunk. It's totally dissolved. Okay, it's with the toluene. Also, you can see it's totally dissolved. So water still has crystal. It's partially dissolved. I can see still there is iodine at the bottom. Okay, this is with the chloroform dissolved, and also in the toluene they are dissolved. In group 3, what we did is iodine, which one was the crystal and solid. So solid nonpolar, we tried to dissolve in different types of solvents, the liquids. Now in group 4, what we are doing is different types of liquids. If they are mixing up, I mean, if they are, if the liquid is, we are trying to dissolve, that means like if you see any layer or no. This is the point to do this experiment. So in group 3, we did the solid thing, tried to dissolve in different types of solvent like polar and non-polar. In group 4, we are trying to do different types of liquids, polar and non-polar liquids, and trying to see that if they're homogeneous or heterogeneous. Homogeneous means we cannot see any layer, but the heterogeneous, we can see the layer. That's what we are doing the experiment. So first thing, it says that water with the alcohol. So I have water with the alcohol. We know that water is polar, okay? And alcohol, which is, I'm going to use the ethanol, which one has the OH group. So both has partially negative charge and partially positive charge. So I'm expecting there should not have any layer, and it should be soluble because they are making, in the presence of OH group, they are making a hydrogen bond, and it should be soluble. So I'm going to mixing up. Okay. Let me use the white pen. So you can see there is no layer. Okay. So it's totally miscible. No layer. So it's a homogeneous. Now I'm trying to do the water with the chloroform. And I'm not expecting it should be miscible because they are not making any hydrogen bond. So chloroform. Need another background. I don't think they can see the layer. You can see the layer? Oh. So there has water and the chloroform. You can see that there has layer, but still I'm trying to mixing up to see that maybe it's soluble. To check. See, still has layer. So water, which is polar, and chloroform which is non-polar, that's why they are not mixing up there. You can see visibly there is a layer. Next one is water with the toluene. Same thing, water is polar, toluene is non-polar. Here you can see the layer, but still I'm going to mixing up. Still you can see the layer. Okay. Next one is alcohol, which is slightly polar, slightly non-polar, and chloroform, which one is non-polar. So ethanol, and chloroform. So you can see there has no separation layer. Okay. Still I'm going to mixing up. No separation layer. So there has like they have intermolecular interaction. Okay. The next one is alcohol and toluene. Sure. No layer. So that means there is an intermolecular interaction because both are has non-polar. And the last one is chloroform. And toluene. This is also miscible. You cannot see any layer. So the principle of this group 4 is when you have polar and polar, you should mix them up. Non-polar and non-polar should be miscible. If you have polar and non-polar, you can see the crystal, the separation layer. Still, you can see the layer because they don't have any interaction. So non-polar and non-polar, they have the intermolecular interaction, so that's why they're miscible. But if you have polar and non-polar, they are not making any bond with the hydrogen. So that's why they are separating it. So this is water and alcohol. You can see that there is no layer. They are miscible. This is water and chloroform, polar and non-polar. So that means it has the layer. You can see at the bottom, it has two different layers. I mean, one layers. This is water and toluene, polar and non-polar again. You can see the layer. This is alcohol and chloroform, both are non-polar. So make intermolecular interaction, they are miscible. This is alcohol and toluene, both are non-polar, has the same reason for miscible. And chloroform and toluene, two non-polar, same reason for miscible. So this is my chloroform. You may think that which one is where, like the top is water or chloroform. So what I'm going to do, if I'm adding chloroform and it stays on the top, my top layer is increases. So that means this is on the top has chloroform. So let's add it. No, my bottom layer increases, right? So that means chloroform density is higher than the water. So water remains on the top and chloroform goes at the bottom. And another one is water and toluene, the third one. You may think like which one is where. Same principle I'm going to use. If my upper layer is increases, that means it's toluene. So adding toluene, you can see the upper layer is increases. That means it's toluene. So water is more dense than toluene. So toluene stays on the top and water remains at the bottom. This is group 5, preparation of saturated solution. We are going to use sodium acetate in a water. So what is the definition for saturated solution? So the saturated solution, it may dissolve the maximum amount of the solute in the water. So after at a certain temperature. So in a certain temperature, it may dissolve the maximum amount of solute. So after that point, it will not going to dissolve any more solute. That's the saturated solution definition. And the supersaturated solution definition is it is above. So it is above the maximum amount of the solute. So if it reach the more than maximum amount of the solute in this solution, so that means it's a supersaturated solution. Here? Huh? Oh, okay. So you can see that there is totally water, nothing is there, no layer, no crystal there. So I'm going to add sodium acetate. I add more. So I put the sodium acetate more. So you can see that it's already reached more than maximum amount of solute, which is sodium acetate. So that's why it's totally crystal. You can see the very good crystal, right? But if I increase my temperature, it should be